Good morning, everyone. As Laetitia mentioned, I'm Raphaël Girardin from Ifremer, and I'm here to present you the work package 4 of NESTORE, where we try to address uncertainties in model and account for uncertainties in offshore wind farm impact assessment within ecosystem model. Most of this work, if it's not all of this work, was performed by a PhD student, Yan-Song Wang, and also the collaboration of a full consortium. When we talk about offshore wind farm effect on marine ecosystem, you have to account for the diversity of offshore wind farm setups, either floating one or set to the bottom, which comes with also a lot of different effects on different compartments of the ecosystem, reaching from change in habitats, from noise, from potential change in turbidity as well, or pollution, and so on. And if you really want to account for all of those, you also need to be able to represent all the ecosystems and all the compartments that will be impacted by those effects. And there is many ways of doing that, and Natalie already presented a lot of those, but you can address that through modeling the full food webs, the entire socio-ecosystem, combining different type of model from biochemistry model to food web models, to exploitation model. And of course, if you want to assess the impact of human activities, and in this case, offshore wind farm, you need also to have a feedback with human activity and way of assessing the different compartments. And with all of that complexity and diversity, you of course, have to consider uncertainty around all the different information you bring and all the uncertainty you have in your model, in the data that feed your model, and also on the outcome of your different scenario that you will try to test. So how many sources of uncertainty you can have in impact assessment modeling? First of all, depending on what is the stage of your plan of implementing offshore wind farm, you will have an uncertainty in the implementation, the type of offshore wind farm you will use, the type of management you will use, and also with that come different type of effect that you could have. So this brings on all the uncertainty you will have in your scenarios that you will try to implement and address through modeling tools. The modeling framework itself, you can have some uncertainty around the input data you used, because you are only partially observing the system, and to calibrate models and to set up those models, the source of information you have is, of course, always biased. You got also some uncertainty around the structure. We already addressed a bit that in the presentation of Natalie. Depending on the type of model you used, you will have different hypotheses and different constraints that will bring also some uncertainty in the answer of your assessment. And of course, for one type of model, depending on the amount of parameters and what type of parameters you have, you will have also some uncertainty that can come with those. Finally, to try to assess the impact of your and the different scenarios you will test it, you need indicators and goals. And depending on the indicators you will use, you will also end up with more or less uncertainty propagated through your whole assessment procedure. In NESTORES, we only addressed few of those. First of all, we tried different type of scenarios of implementation of offshore wind farm, but also management within offshore wind farm. We try with the different models available to address the uncertainty around the structure by comparing ecosystem model on several scenarios. We started to address parameters uncertainty through testing the sensitivity of our model to parameters. So knowing which parameters are the most influent in our system and which will be affected by offshore wind farm, and how that will be translated to the assessment of offshore wind power impact. And of course, we explore several indicators to see how robust they are to uncertainty. So first of all, to address scenarios uncertainty and management uncertainty, all the work was evaluated on the case study of the Eastern English Channel, and we try to assess the effect of offshore wind farm throughout its life cycle, from construction phases to operational phases, with only 3 different effects tested: noise emission, sedimentary suspension, and also different management strategy for fishing within the offshore wind farm. So close during construction phase, and several different fishing regulation. The choice of effect was mostly dependent on the model used, that I'm going to show you a bit later. Regarding the different scenarios tested, we applied different type of offshore wind farm deployment that were based when we worked on it on maps developed by the Syndicat des Énergies Renouvelables that try to balance different goals, either reducing the cost of energy, trying to avoid protected area, being far from shore, and also a scenario balance that try to account for all of those different components. And also trying different scenario for fishing within offshore wind farm during operational phases, either no restriction, depending on the type of offshore wind farm that can occur, closing for active area, mainly trolling, and no fishing within offshore wind farm. And to try to address structure uncertainty, basically, we used 2 ecosystem models that were developed and further developed within NESTORE, as already mentioned by Nathalie. Osmose, developed by Yan Sang-Wang, and the ecospace model of Southern North Sea and Eastern English Channel, developed by Emma Arrhenius and al. And basically, as you can see here, is just a brief overview of the main differences that you could have between different models. Osmose is trying to track fish schools, and is an individual-based model, so meaning that he tried to capture all the life cycle and biological processes around those fish schools, mortality, growth, reproduction, rather than ecopass ecospace that will represent the ecosystem through species or functional groups and track the whole biomass of the full groups. You can have change of range in space and time for those models, different biological groups used, different fleets, of course, and also here a different species movement hypothesis, like in Osmose, a stochastic movement within the area of distribution, or more biological or predation habitat preference dependent in the area. And so all of those different in structure will bring different results and different uncertainties. So for the first result I'm going to show you here is the result on the ecosystem model Osmose, where we try to explore all the different implementation strategy of offshore wind farm, and also all the different management strategy for fishing during operational phase. So to read this figure on the top, you have all the scenarios during the construction phase, on the bottom after the construction phase. And so the effect only apply on the food web during construction phase. Each column represents fishing scenarios during the operational phase, and each box blocks represent different type of implementation scenarios. And here I'm showing you the effect on the biomass, on the total biomass in the system compared to when there is no offshore wind farm. And basically the main outcome that you can see here is that in all different scenarios, you see a decrease of biomass in the model when you apply some noise effect and some sedimentary suspension effect, with various degrees of amplitude depending on the scenarios, of course. And one key result also in osmosis is that this effect propagates through time. Even if the construction phase stopped, you can see that biomass decrease with some level of decrease that depend also on how you will manage fishery. And of course, when you move to the same representation, but focusing on the yield, so the catch from the fishery, you will see that at short term for fishery, there is not that much change in catches, and even sometimes some slight increase, but not really significant. But on the longer scale, you can see a decrease in yield and higher decrease in yield when closing fishery within the offshore wind farm. So less the biomass decrease less when you close fishery, but at the cost of having a bigger loss for the fishing sector. If now we compare on the balance implementation of offshore wind farm, the two models, so osmosis and ecospace, you can see on biomass kind of the same picture, basically, an overall decrease of biomass in all the different scenarios. But one key point here is you don't see exactly the same thing at long term with a model ecospace that go back way faster to, I would say, normal status compared to osmosis that will propagate a bit more the effect through time. And those come from, can come from different hypotheses in terms of how fishes are distributed through time, the biomass is implemented in a model, and how the cohort is implemented in a model, basically, and so come the uncertainty around the assessment of the impact you will result in. Moving on now to the uncertainty around parameters. So we start to touch base on that by going through what we call a sensitivity analysis of ecosystem model. And here we only focus on osmosis. So basically what the principle of this is, you try to perturbate the parameters and see how much the perturbation of your parameters will impact the outcome of your model, meaning the biomass, the yield, or any output that you can have in your model. In osmosis, this means try to perturbate nearly 200 parameters governing growth, predation, mortality, and fishing. And basically, if you try to do that in a normal computer, you end up with 10 to the power of 172 years of simulation, which is basically impossible to reach out. So you have to come up with some way of reducing your simulation time through factorial plan, basically. And we managed to do using Morris one at a time technique, reducing the simulation to 2 millions, and also by using a supercomputer to reduce the time of calculation to 2 to 3 weeks. And basically, here is really an overview of the sensitivity of a model to different types of parameters. On the left side, I'm presenting you 4 indicators that you can build from osmosis. Basically, the mean length of all the fish within the model, the mean trophic level, the total biomass, and the total yield. And you see in each box plot how much each parameter type will impact your model when you perturbate it. And the main outcome from that sensitivity analysis is that growth, all parameters that govern growth are impactful for the model and for any type of indicator coming from this model. Predation also and prefill will also have some impact, and mortality will have really a contrasted outcome depending on the indicator you used. And so basically, depending on which effect you will consider, which effect of offshore wind farm or any human activities you consider, and which process in your model it will affect, you won't have exactly the same outcome depending on the indicator you used. So this is also something to keep in mind. On the right side is an overview of which species is the most impacted by the perturbation in our model. And we can see that in osmosis, depending on the biomass level of a species, we see 4 main species coming out: the mackerel, the laser-spotted dogfish, the whiting, and the herring. Basically, any parameters that are perturbed for the species will have an impact on the outcome of osmosis. And of course, any effect from human activities that will affect those species will end up with an impact also on the system. So take-home message, basically, even if you account for various uncertainty and various outcome, you still end up with an overall effect of noise emission and sediment suspension that lead to a small decrease in biomass when you implement it through species displacement. Fishing closure might temper that impact. However, this will come with a greater loss for the fishing sector, of course. The model structure uncertainties led to a more or less persistent impact of the construction phase. You have a small decrease of biomass in both model, osmosis and ecospace. But when looking at longer term, you might end up with different results. And so this is also something to consider. You might have an impact that is between both models, or maybe you need to bring another model to also balance those results. And of course, any effect on growth, on herring, on all of the species I mentioned before, are most likely to have an impact in osmosis and in the system at short or longer term. This work brought a lot of questions also, and future work needed. Basically, we only represent here 2 effects and address uncertainty for those. But to really properly account for all the different effects of offshore wind farm, we need more development in models, and also assessing uncertainty in the data used for implementing those models. We need model on hydrodynamics, also biochemical cycle, a better representation also of modification of the impact, but also fishing behavior to address also the impact of the different effects on those compartments. The outcome of the sensitivity analysis could tailor a full uncertainty propagation analysis by allowing us to focus on parameters the most sensitive in the model, to reduce the number of parameters we will try to propagate the uncertainty from, and then try to have a full propagation of uncertainty that will allow for risk assessment in management strategy evaluation and no longer only focusing on the main effect, but also accounting for risk related to uncertainty in model structure, in scenarios, and so on. Beyond NESTORE consortium and the help all of its members, I also want to thank a lot all the R&D colleagues that support that work through help in Osmose and the development of Osmose. IFC Graduate School also give us some additional funding, and none of this work would have been done without the data. So thanks to ICIS, to the SIH of Ifremer, and also the Flotte Oceanographique Française for the data provision. Thank you for your attention, and if you have any question, I will take them at the end.